Hello everyone, welcome to the webinar looking at the fundamentals of LTE radio planning and optimization, brought to you by the Telecoms. My name is Nikki Rankin and I'll be your host for today's session. First things first really, I'd just like to go over some quick maintenance items. First of all, if you experience any difficulties with audio or advancing slides, refresh your screen with F5. And also, if you are experiencing other issues, hit the question mark button to receive assistance, and we will try and help you out. At any time during the presentation, submit your questions into the Q&A window on the left-hand side of your screen. And it's also worth noting that if you're interested to hear this webinar again, we will be making a recording and we will send this link over to you for to download it within the next few days. So let's begin by introducing our speaker. So today we're really happy to be joined by Dave McNally. Dave has worked in telecommunications since 1986 now, I believe, and now heads the development and delivery of LTE communications portfolio for the Telecoms and Tech Academy. So thank you, Dave, for joining us today. And now I'll hand it over to you to begin the presentation.
Yeah, thanks, Nikki. Yeah, hi everyone. Good attendance today. There's a couple of names in that list that I recognise as well. So if you already know me, hi, welcome to this session. So we've got about 30 minutes or so today, just to kind of give us a quick overview of what it means to do LTE radio planning. And as Nikki said, if you've got any questions as we go along, hit those up in the question pod, and we'll deal with some of those towards the end. Right, so we've yeah, just not a lot of time today. So what we're going to try and do is we're going to take a bit of a phased approach to the planning. So we'll discuss information that we need to do some planning, and how we might use that information to do some initial modelling of a system. Then we can get to a little bit further and talk about things like link budgets and capacity modelling. Now, in the initial phases of planning, we really need to do some sort of basic modelling just to understand what all of the variables are and how those variables might affect the planning process. But ultimately, when we get around to doing some serious planning, we need to kind of break out some expensive software planning and look at those particular processes. So what information do we need to do software planning, and what might the expected outputs be? And of course, once you've built the network and you're running the network, we need to consider things like performance optimization. So what do we need to do in terms of building a system, measuring the performance of that system, and then how would we optimize, and what should we be optimizing against? So some performance KPIs. So we'll jump straight in. Now, really what we're going to do over the course of this session is we're going to look at 4 different phases of planning. And obviously, in a real case, there'll be many more phases of planning with a lot more detail in each of the sections. Yeah, 4 phases breaks down quite nicely. So in phase 1, one of the main activities that we need to do is to get information. Now, that information will be used to drive any initial objectives that we might have from the system. Now, I guess one of the major outputs or results that we're looking for from this sort of first phase of planning is to answer the question, how many base stations or eNode Bs do we need to satisfy a number of objectives? Now, those objects ultimately are going to come down to some form of capacity definition and some form of coverage. And there are lots of different ways of stating both capacity and coverage. It's rather hard these days, certainly with sort of data-oriented systems like LTE, to separate the two. I guess back in the days of GSM and even GPS, you know, we could probably focus on just the coverage and then try to work out maybe what the capacity would be. But these days, when we're building high-capacity networks like LTE, and of course with services like 5G, the thing that we tend to focus on is that of capacity. I mean, it's there because we want, you know, many tens of megabits per second. But it's interesting to understand how the work that we do to create coverage, how that impacts capacity, and the work that we do to optimize capacity, how that might in turn affect coverage, because the two things are, you know, they're linked extremely tightly. But in any case, however you define those objectives, in simple ways or more complicated ways, really what we need to do from this first phase is to get a benchmark or an estimation of how many base stations do we need to satisfy those objectives. And that has to be, getting information like what radio spectrum are we going to use, how big will the radio channels be. And that means that we can start to model the network, and we can do some basic link budgeting. We can do some capacity-based modeling that might answer that question. Now that this the number of base stations that we think we need, if we do the calculations for how many base stations do we need to solve a capacity problem or a coverage objective, those two numbers that we're going to get will likely be very different. So again, part of the optimization process or part of the initial modeling process is to look what the optimal number of sites would be to get 90% of the capacity or 90% of the coverage. The second phase that we would move on to, once we have a rough idea of how many base stations we think we're going to need to meet the current objective, then we need to go and find the sites, the physical locations where we're actually going to build the base stations. Now, ultimately, what we're going to do is we're going to co-locate. There may be occasions, of course, when we get down to things like small cells or femto cells, where we need to discover or find new locations for new sites. But the initial plan of a system will undoubtedly be co-located with the existing network, if there is one. But it's interesting to note, if we have a pre-existing 2G or 3G network, clearly we're going to have some site locations. But it'll be interesting to see, based on our assumptions and objectives from our LTE planning in phase 1, what the difference would be between how many LTE sites we need versus how many current locations do we actually have. And given that there may be some differences in the spectrum that we're using, it's quite likely that the total number of sites that we need to build the LTE network to our objective will be a greater number than the sites that we currently have. Now, then you have to start the process of finding a site and then get the lawyers involved and so on. Find the rooftops, do the surveys, and then it gets a bit more complicated, a bit more time consuming to do that. Now, before we jump on to phase 3 and phase 4, let's just take a little closer look at what we mean by information gathering, initial objective setting, and we'll have a real quick overview of things like link budgets and so on. So information that we think we need. Now I've got a bit of a curious title in this picture. So there's generally known data. Now that almost sounds like there's a question mark after that. Are these things that we know? And you would certainly expect from an operator's perspective that we should know what frequency band we're going to be planning the LTE network in, or indeed how much spectrum we have, the amount of allocated spectrum that we've got to plan the system. But that's not always the case. When we start refarming spectrum, for example, now you may have already built a network based on 1800 megahertz, for example, but you may be considering refarming the 2100 spectrum, or perhaps you've recently acquired some 700 or 800 megahertz spectrum. You might want to play around a little bit or experiment with what the system performance would be in different frequency bands. Now, the phase 1 process is a very low-cost process. You're not buying base stations, you're not buying equipment, you're not doing site surveys and so on. You can do the whole thing with pencils, papers, calculators, and of course, Excel and other software-based tools. So you're not spending an awful lot of money doing this, and it's a great chance to test the performance of the system under different conditions. What if we use 1800? What if we have to use we move up to 2600? What if we use a 10 megahertz channel? What if we use a 20 megahertz channel? So we can test all of those assumptions and get a real good feeling for how the system performance might vary if we change our assumptions. So this is stuff that we would kind of, we could certainly write down a whole long list of actual facts. It will be the 1800 megahertz spectrum. We will be using a 20 megahertz channel, and we can start to talk to the vendors about what equipment performance will be. So, we get the antenna catalogs out. We talk to the vendors about their base station equipment, what the power outputs would be, receiver sensitivities and such like. So we can get the spec sheets for all of the equipment and start putting together these models. Something that might be a little harder would be sort of the market research stuff. So we might have a pretty good idea of where the service needs to be, so the service area. But then we might need to start looking at some sort of, social science stuff, if you like, population density, demographic, the expected penetration, what the market looks like, what the expectation of service might be for that particular population. Now, these are quite hard things to measure or to predict successfully, because they change over time. And I'm sure we've all seen the graphs that basically do this. Okay, so you're looking at time scale here and the amount of capacity that's required by the network. We may be in a planning phase, somewhere along this level here. Okay, during that particular period of time, you're looking to launch the network at some point further in the future. But in the planning of the system, when we're considering things like capacity, certainly, we might need to be thinking a lot further up this line, because if we plan the network for, let's say, this amount of capacity here, then the network will be broken or will be performing badly in the next phase. So whether that's a year or a quarter of a year and so on. So we need to look quite carefully at these predictions. I mean, we all know that the graph is going to point upwards, but it's what the gradient of the graph will be and over what particular time scale and so on. We know there's a capacity issue because more people have smartphones, and those smartphones do more clever things. They demand more data, and that's one of the reasons why we're now talking about and building 5G networks, because there is a sort of a point at which LTE, if you like, basically tops out. There's no more capacity that we can get from LTE. So we're investigating, or we've built new technologies like 5G to hopefully get us into the the next sort of 30-40 years or so. So a lot of the stuff that we have here, I think particularly in the market research, they are assumptions or educated guesses, and that's one of these cases where you need to test. Okay, what if? What if we have a fantastic marketing campaign and we get 50% of our expected a demographic? How does that change the performance of the network? Do we need more base stations, less base stations? And we're going to talk about things like link budgets and so on in a moment or two. But there'll be other people, not necessarily the engineers, but there'll be other people who are managing different kinds of budgets and restricting the amount of money that we think we should spend on buying and building base stations and so on. So of course there's an accounting budget that needs to be thought about in this respect as well. Not something that we're going to worry about in this session, at least. So part of the modeling process, once we have an idea of what equipment performance looks like, both on the transmitting end and the receiving end, we're able to start doing some link budgets. Now, the principal result that we want from the link budget is to calculate a value called system gain. And system gain is a number that tells us how much energy or how much power do we have to play with in designing the system. And it is the system gain that will determine either the cell radius or ultimately what the capacity of the system will be. Now, to arrive at the system gain, clearly there are some calculations we need to do at the transmitting end. So in this case, the base station, the E node B, we try and find out things like what the transmitter power output is. And we take into account any losses that might be present in that system through filters, feeders, connectors, and so on. There may be a gain associated with the antenna system as well. At least we hope there will be a gain associated with the antenna. And we may take into account some other sort of special things like diversity or multiple antenna gain to arrive at a maximum power point that we refer to as the effective isotropic radiated power, the EIRP. So that in a way would be the maximum energy available to us in this particular system. And of course the energy at the antenna is a direct result of the transmitter power, the losses and gains in that particular system. Now, because we're finding the maximum energy point in this system, we also need to find the minimum energy point, and that of course comes from the receiving end, in this case the mobile device. And to find that, we need to understand what the receiver threshold is, receiver sensitivity, if you like. Now, in all of the variables in this system, receiver threshold or receiver sensitivity is probably the most complicated part, because receiver threshold is dependent on the modulation and coding scheme that the system supports. Now, in the downlink with LTE, in our basic, should we say, release 8, release 9 LTE, there are 29 different modulation coding schemes that we could consider, and therefore 29 different receiver thresholds that we might need to consider as well. Effectively 29 different downlink budgets that we would need to do to work out what the system gain would be for 64 QAM versus a QPSK based.
Yeah, sounds fine. It's clear.
Yeah, hi Paul, we can hear you too. Okay. Yes, so receiver threshold is probably one of the most complicated variables that we have in the system. And in calculating the minimum power point, or in this case, the isotropic receive level, we need to take into account that sensitivity, the losses due to feeders, connectors, and so on, and any gain that might be present in the receiving system. Now, in the case of it being a mobile device, losses due to feeders, connectors, filters, and so on is likely to be a very small value, and the gain of the antenna itself on the mobile device is not particularly good, and maybe would assume something like a unity gain in that case, something like a 0 dBi gain, and that would be about as good as it gets in that case. So IRL is our minimum power point, EIRP is our maximum power point, and of course the difference between the two then is the system gain, the amount of energy that we've got to play with in the system. Now we should do that in two directions, of course. So we would calculate a system gain in the uplink direction and the downlink direction, and the formula would look a bit more complicated like this, but it's relatively straightforward. So long as we understand the equipment performance, we've spoken to the vendor, we've looked at the spec sheets, we've done maybe our own calculations to work out what receiver threshold might be. That might be quite important as far as the base station is concerned, because in the uplink direction, the receiver, the actual sensitivity of the receiver may be dependent on the passive and active components in the feeder system, so running up to the antenna and any feeders and connectors and so on that might be here. So the total sensitivity of the system is something that we might need to be able to calculate. Depends on the vendor, depends on the arrangement of equipment on the tower, whether there are tower top equipments or whether we're still using RF type feeders and connectors and so on. Now, once we calculated system gain and we have a number, and that number might range anywhere between, say, 140 to 160 dB, for example. I've not put any numbers in here, but that might be a typical range. We've then got to work out how to, well, the system gain, the number that we have here, effectively is the budget. And now what we need to do is to work out how to spend that budget. Now, ultimately, system gain will be converted into a distance one way or another, but we need to spend some of that energy budget that we have on overcoming impairments that will be present in the cell. So that might include things like fade margin. Okay, now slow fade margin, reliability or availability margin, they're all kind of the same thing. But typically we'd include for something in the order of, say, a 95% availability across the cell. So that will be an area. An area availability, we would need somewhere in the region of sort of 8 to 12 dB to compensate for fade and shadowing that might be present in the cell. So we're going to spend 8 to 12 dB from the system gain. Then we would need to consider whether building margin should be included. That would be there's a very large range of building attenuations. It's very dependent on the nature of the building materials. And whether or not you would include a building margin in the link budget is something that needs to be considered as well. So clearly, if you're designing a downtown system and you had the planning objective to ensure that there was 70% coverage in all of the buildings in the downtown area, you're going to have to include that building margin, that attenuation factor. But you can see that it also spends the budget. It may take a very large amount of the system gain from us. And we might include things like body margins, and there'll be maybe a few other margins that we would include in there as well, depending on the scenario or the situation in which we're planning the system. Now, what's left over? So we have our initial budget. We spend some things on impairments. What's left over here? The maximum allowable path loss or power loss, if you prefer. This is the actual number then that we would convert into a distance. So we've worked out what the maximum allowable path loss is by working out system gain and subtracting from that impairments. And then we need to choose a propagation model, which will then convert our remaining power into a distance. Now, there are many propagation models, Okumura-Hata, Wallfish, Ikegami, some proprietary models that you'll most likely find from the software tool vendors. Regardless of which propagation model you choose to use, the propagation model will require additional inputs. Things, for example, like what frequency band are we using, what type of clutter is present, maybe some terrain information, certainly antenna heights would have to be included in that. So the problem with the propagation model is it doesn't really matter which one you choose, so long as it's it's been selected for the frequency band and maybe the type of environment. But you could choose 10 different propagation models from 10 different places, and with exactly the same information going into them, it's going to give you 10 different distances at the output. And the big question, as always, is which one is correct, which one should we use? And that's something you would need to consider both in terms of sort of the phase one simple modeling that you would do. I mean, sure, use Okamura-Hatta, or COS 231 maybe, if that's more appropriate. Use the model which is appropriate to your scenario, and make comparisons. It gets a bit more complicated when you move towards a software tool, because you need to make more complicated decisions about which propagation models and how to tune that model and so on a little later. So we have the distance in the end, and that will be your sort of nominal cell range. Remember though that whatever you think the distance is, so we draw a little sector here, whatever you think that cell radius is, okay, that was based on either an uplink or a downlink system gain, okay, and don't forget that in there was the receiver threshold. Okay, so when we calculated the system gain, there was a receiver sensitivity in there, a threshold, and if we based that on, say, something like KPIS, which has a very good sensitivity, then we're going to plan a very large cell. The distance will look good, okay, you're maybe 1 or 2 or 5 kilometers. But if you were basing this particular part of the modeling on, let's say, 64 QAM, well, the sensitivity of a 64 QAM receiver is much worse than QPSK, and that will significantly reduce the system gain, therefore the allowable path loss, and therefore the distance. So if we were doing this properly, then of course what we'd be doing in the downlink direction is we'd calculate 29 different link budgets, we'd calculate 29 different distances, and we would have a rough idea of just how much coverage maybe we'd get out of each and every one of those modulation and encoding schemes. Now, I would never suggest you do that with pen and paper. This is what Excel is for. You can push that model, those calculations into Excel, and get that tool to work for you. Now, the link budget part is principally about how big can we make the cell, but the discussion that we've just had, saying that the cell edge, how far away the cell edge is determined by the sensitivity of the modulation coding scheme. So 16 QAM, QPSK, and by using those terms, we're in some sense talking about the capacity of the system as well, because whatever modulation coding scheme is available to us at the edge of the cell will overall determine what the total capacity or the average capacity of that cell might be. Now, it's far too simple just to say, well, LTE with a 20 megahertz channel can do 100 megabits per second, 100 megabits per second plus, and then you put some fancy antennas on there, things like MIMO and so on, and it gets even better than that. It's a bit of an oversimplification and an overstating of the performance of the system, because when you do the link budget, of course, what you determine is that the parts of the network, or the parts of LTE that support the highest data rates, things like 64 QAM, for sure, you could do 100 megabits per second plus in this part of the radio cell if you were the only user in the radio cell and connected to the base station under the best of signal conditions. But if you move further away, of course, signal to noise is going to get much worse, and you have to sort of downgrade the transmission to 16 QAM, and you move even further away, and you have to downgrade again to QPSK. So it's complicated by the fact that we've got adaptive modulation encoding, and it's further complicated by the fact that we've got many users in many different parts of the radio cell. So trying to work out what the overall capacity of the system is a little hard to do. We need to kind of do fairly complex modeling, make assumptions about what each of the users are doing in their distribution throughout the radio cell, and so on. Now, it's possible in spreadsheets to calculate very simply what the total maximum or peak throughput might be. So this is just a screenshot from my spreadsheet, where you can see in the downlink direction here, we've got our 29 different modulation coding schemes here. So we've got the modulation scheme and then the code rate associated with that. We've got as well a calculation of the sensitivity that each of those modulation coding schemes can support. So you'll see that the most robust QPSK one is not too bad at something like -100. This, by the way, is for a 20 megahertz radio channel. And then we can do a calculation to work out what we think the total bit rate might be. But then we have to take into account some overheads, physical layer overheads, signaling overheads, and such like. So the slowest it will be, so remember this is a 20 megahertz channel, is going to be around about 2 megabits per second, which doesn't seem particularly efficient, but it would be fantastically robust, and you would be able to build a very big radio cell because the sensitivity is pretty good, and the modulation and coding scheme lends itself very nicely to working in noisy or interfery type environments. Whereas if the objective was to have a very high capacity system, you need to, of course, move to the bottom of the table, where you see that you might, in theory, get something like 75 megabits per second, but once you've taken into account some of the protocol stack overheads, that might be closer to sort of 50, 60, 65, something like that. But also note that the sensitivity here is much worse. It's about 30 dB down from the most robust modulation scheme. So 30 dB difference in the link budget means that there'll be a significantly less system gain to play with, and of course the distance of the cell, you may be talking now about a couple of 100 meters of usable cell range, depending on your assumptions of fade margins and so on. So yeah, you put that into a complicated system like this, where you've got some people, some users in good locations and some users in poorer locations as far as signal to noise is concerned, then it becomes extremely difficult to model the capacity of the system. You have to make some statistical models or make certain assumptions about the distribution of users in the cell, and so on. The other thing that's worth mentioning here as well, albeit very briefly, is saying that there is something in the base station called the resource scheduler, or the scheduler, that has to make a decision about which of the users we should allocate physical resources to, because there is a finite amount of physical resource in terms of the time domain and the frequency domain, and we need to decide on what percentage of that physical domain should be presented or granted to each of the users in the cell. And the decisions that the scheduler makes, or the manner in which the scheduler has been tuned, will have a massive effect on the average and peak throughput that you would experience from this radio cell. And the scheduling algorithm, the thing that thinks about this and does those calculations, is quite likely going to be very different between different vendors of base stations. So even under an identical sort of traffic scenario, the total capacity or the peak and average capacity that you see may be different for different vendors. Just an interesting thing to know if you're in an RFP, if you're talking to the vendors. Might be interesting to line the vendors up against each other under a typical traffic scenario and see which is best for you. It's very hard to say that one is better than the other, but whatever's better for you, whatever your system objectives are, it needs to be kind of at the heart of the planning process, so that we are able to optimize the system against our expectations. Something that we can do in that sort of simple modeling scenario as well is that once we've got all of the link budget and capacity assumptions sorted, we can start to think about what kind of users do we have in the system. And again, we don't have to be too complicated about this, but it's possible to start counting the number of sites. Now, this particular model projects over a 5-year period based on an increase in the number of customers and an increase in the amount of data each of those customers use. And we can see that we get very different numbers. In fact, in year 1, let's say, we just take that first column there, we need 298 sites to cover the projected area, whatever the area was in that sheet. But to meet the capacity objective in that same year, we would only need 48 sites. Now, clearly, if we only build 48 sites, we're never going to achieve the coverage that we need, because the model tells us we need closer to 300 sites to achieve that coverage. So that means that in that early part of the project, we're going to have a massive oversupply of capacity, but it's necessary to achieve the desired coverage, the coverage availability, reliability, and so on. Now, one interesting point to note here as well is that coverage curves like this, the number of sites that you need for coverage, always tend towards a flat line, because once you reach 100%, well, you don't need any more base stations. The capacity sites, on the other hand, always tend to be a little bit more inverted, because the demand for traffic, you know, through applications and phones and subscribers, the demand continues to increase on a, you know, a more or less exponential basis. So the number of sites that you need continues to increase. At some point, your capacity curve will overtake the coverage curve, and now you're building or optimizing the system for capacity, no longer for coverage. So it's interesting in a system to calculate the point at which you need to start focusing more on capacity than coverage, and depends on your assumptions of the market and so on when we do that. So a lot of the work, as I say, in phase one, mostly in phase one, you know, you can do it from Excel, you know, pencil, paper calculators, that kind of thing. But at some point, you might want to verify a lot of the assumptions that you have made by incorporating some more real-world aspects. Now, I'm not suggesting that you do your phase one modeling and then you run out and build a system. You might want a bit more information than that. So this is where we start off with the software modeling. We use much more sophisticated modeling tools that may be able to confirm the assumptions that we've made. So once we've introduced some real-world data, is it still possible to satisfy the objectives with the number of sites that we think we need? So, I mean, the software planning process, again, is a phased approach. You need to do that initial objective setting as well. And your objectives may have changed. By the time you get to this point in using the software tool, you did your model one objective setting, you tested a few different scenarios, and your objective now may have changed. So you need to have a clear set of objectives at the start of this process. Again, to drive the software tool, typically you need a bunch of vendor-based information, so what the eNodeB and UE capabilities might be, any specific vendor features that might be present that you can incorporate into the tool's modeling process. And then you need to test the modeling process, you know, choose a propagation model, tune that propagation model, and then run some detailed planning well, look at the outputs, see if the outputs based on this real world information, or as real world as we can make it, we're still able to meet those objectives. This is where it gets complicated and expensive though, because in order to drive these tools, you need a lot of expensive data. Now, the actual software modeling tool itself may not be terribly expensive, but once you start asking for things like digital terrain maps, okay, particularly those that have very high resolution, or clutter maps, 3D building topologies, and traffic maps, the purchasing of those can be extremely expensive. Depends on the resolution and the area and the sheer volume of information that you need. But honestly, you can't really run a decent plan in any tool without without detailed and high resolution information. The smaller the radio cell that you are planning, the higher the resolution the information has to be. So if you're planning macro cells, which you expect to be in the order of 10 to 20 kilometers, well, you can probably get away with maybe 20 or 30 meter terrain and clutter. But if you're starting to you're trying to figure out where to deploy a radio cell that will only cover maybe a radius of 250 meters, then clearly you're going to need 1 meter or sub 1 meter terrain, clutter, and even 3D building information to be able to plan that system properly. And the problem becomes a three-dimensional problem as well once you start incorporating things like buildings. So of course, you can get this information from many different sources. Your favorite software tool vendor may well have a shop that you can buy this stuff from, or you may choose to get this from an independent third party. That would be entirely up to you. But of course, the good thing about the tool is it can give you a lot of information when it comes to the prediction and the analysis stage. Now, on the training courses that we run, we use well, I still call it Mentum Planet. It's certainly a bit of software called Planet. The company is now owned by InfoVista. But this is typically one of the output screens that you would see. But you could see, in terms of sort of overall network analysis, you can see that there's lots of different analysis layers that you can look at, and the tool has got sort of fairly powerful statistical measurements that you can add to this as well. So you can kind of make and compare lots of different analysis layers to make sure that you're achieving the particular objectives that you're looking for. Typically, what you might look for is something like RSRP in terms of coverage. You might be more interested in things like RSRQ. You could also be more interested in things like what the maximum achievable data rates might be. So you can present that information in a very meaningful way by looking at the colourful pictures that it draws for you on the screen. I think this particular output, in fact, was an SINR output or analysis layer. Of course, you do your homework. You buy an expensive tool. You buy some very expensive databases to do your predictions with, and then you want to go and build the system. Now, a lot of these software tools as well have a very, very useful feature. Maybe not part of a phase 4, but there's like a pre-build optimization, because once you start building the thing, once you start buying physical equipment and doing the installation, that's where things get really expensive. And to be perfectly honest, in order to be economical in the deployment of the system, you never want to revisit the site. You want to go there, install the equipment, hang the antennas, connect everything together, walk away from the site, and never really have to visit it again. Certainly not in a human capacity. You don't want to go back there and be climbing the towers and so on, because it's expensive and dangerous and so on. So that means that the build configuration of each site needs to be known before you build the site. So, in which direction are you going to hang the antenna, for example? What power output should we use? How high or low should the antenna be? Now, this pre-build optimization is something that a lot of the software tools will do these days, in that you can set it an overall objective of improving coverage or reducing interference or maximizing throughput. And what the tool is able to do over a certain number of sites or a cluster will be to recommend antenna orientations, heights, and powers. So you already know how to build the network before you've ever picked up a spanner to actually go and physically build the thing. And that's an extremely useful thing to do. And again, the joy of software tools and spreadsheets and models like this is that you can do variability analysis. You can say, well, what if these conditions change? What if this happens? And you can do this over and again. And the only money you're spending really is the time to run and to drive those tools. But at some point, you're going to go and build the thing. You are going to build a tower. You're going to hang an access point off a street lighting pole or something, and then you need to work out whether or not all of your assumptions, predictions, and modelings were correct. And that almost certainly means that you need to go out and take some measurements, either physically go out there in the environment and drive test an area, or just take analysis directly from the access points and base stations themselves. Most equipment, of course, will come installed with probes that we're able to extract information and to do some sort of your live optimization of the network, if you like. But the optimization activities, well, we could typically push that into 3 different levels. The site level here really is this is the building of the network, or rather the building of the site. So we've got site and sector level commissioning, which is the installation and integration of the equipment, connecting everything together, powering it up, make sure it works, make sure we've installed it correctly. Okay, doing some standing wave tests on the RF system, if there is an RF system, verifying the installation of the antenna and so on, and maybe also verifying the many parameters that will be installed as part of the base station, things that determine cell selection, reselection, the handover and mobility parameters may be something that require at least checking. Most of those will be factory default, unless you've made some specific instruction to your vendor to change the values. But there are many of these parameters, and part of the optimization process is really to make sure that those parameters are set correctly. And if not, because when we do the drive test, we find out that handovers don't work, or sites are being ignored, maybe by the mobile equipment. We need to go back in there and make a change to those parameters to change the behavior of the system. So clearly, what we'll do is we'll build the first site, 3 sectors maybe. And then we do cluster level testing. So it's at this point maybe where we can do some additional throughput testing, mobility testing, of course, with things like handovers, moving between different cells and clusters, connection testing, latency, and the overall drive testing in that area. So you might do that cluster by cluster, and then of course you start building out the clusters and doing more extensive drive and range testing. Now, as well as the environmental testing that we'll be doing by going out there with real radios and taking real measurements, the overall network performance will be monitored on a continuous basis as well. So we'll be looking to see how the traffic moves in the network, where the hotspots are, what the what the customer experience might be. So there's a market level process that we need to go through as well. That market level process it forms part of the initial assumptions back in phase one. What did you think your customers wanted? Did they want the highest possible peak throughputs, or did they just want a 5 megabit per second 100% reliable type of a service? So that assumption needs to be compared with the user experience once we've built and joined and integrated all of these systems together. And of course, in drive testing or in probe testing, we may need to make some changes to the network. We can do a lot of that through the antenna. We can tilt it, we can rotate it or rotate it in the azimuth. These days, certainly with newer builds, it's most likely to be an electrical process that we can use, so remote control antenna effectively, where we can change the tilt and the azimuth. Now, by how much should you tilt the antenna, or by how much you should rotate the antenna? Well, that again is going to be dependent on software modeling. You can make sort of basic recommendations that you think there's too much interference, we should tilt the antenna down, just to change the radiation center of the antenna. But remember, in a live system across a cluster, that one change that you make to that one antenna will have an effect on all of the others in its path as well, which is why sometimes we would prefer to do the optimization modeling in software to see what the wider impact might be. Sometimes we're trying to improve coverage, sometimes we're trying to improve capacity, and of course there are various ways in which we might either measure that or how we might make changes to it. Some typical numbers here maybe in terms of optimization targets. I mean, these might form part of the sort of initial assumptions as well. Things like cell edge throughput at 5 to 10, RSRQ, we've not really gone into and defined what these parameters are, but something we would do in a 5-day training course. Of course, we would spend a bit more time on that. RSRQ -7 is good. RSRP of better than -75 would be okay. Signal to noise measurements as well, better than 13, which kind of drives us towards the sort of 16 QAM modulation coding schemes. And area and edge availability would be figures that you might consider as well. I guess once you get up to the sort of cluster level again, and this is sort of the market level KPIs, on a continuous basis, we'll be measuring things like the connection or call success rate, the drop rate, the uplink and downlink throughput are things that will be managed all the time. We'll be looking for trends over time, the differences between peak hour and off peak. Things like latency as well might be or is increasingly important for more machine-led applications, and mobility-based KPIs as well. Now, exactly how you would optimize for, if the call drop rate or connection drop rate was not as good as you want it to be, or the average uplink throughput was not as good, this is where the optimization process starts. And there are many parameters that you might look at, including the basic antenna tilting, but there's a lot of software-based parameters that you might want to consider in terms of optimizing for a specific performance goal. Now, we've probably gone a little over time, but that's pretty much all we have time for today. But just in case you might be interested, which if you're on an LTE radio planning webinar, you might be interested in this. We're actually running 2 5-day courses in the near future. 8th to 12th of April in London, we've got a 5-day program, and also in Johannesburg from the 20th to 24th of May. Now, in that course, we basically do what we did in 30 minutes, but we do it over 5 days. So there's plenty of time to talk about both the theory and the practice of planning LTE systems. So what that course is basically going to cover a bit of core network and air interface theory, because it's always nice to know that stuff. Link budget theory and practice, capacity modeling. Some of those spreadsheet screenshots that you saw popping up here will be using modeling tools like that to demonstrate how we would perform the planning. A bunch of scenario-based exercises, practicals using modeling tools, and hands-on as well with the radio planning tool, so you can get a real good feel for the difference between modeling in Excel and modeling in a more expensive software tool. If you want to know more about that, of course, you can find us on the website, or you could perhaps email Nicole, and she'll have more information about those dates and how to book and so on. But that's pretty much all I've got time for. I think we've got maybe 1 or 2 questions. I can see at least one question there from Elias. So will these models apply to 5G planning? Elias, that's a really good question. Yeah, 5G is, well, it's a lot more complicated, shall we say. If we're going to deploy 5G in similar frequency bands, let's say the UHF band, so 300 to 3000 megahertz, many of the planning processes will from LTE will more or less apply to LTE to 5G, because we're still talking about the same wavelengths. It's fundamentally an RF problem that we're trying to solve. Where it gets a little bit more difficult is when we start introducing the capacity. Okay, and where it gets even more difficult is when we start using different frequency bands. So once we go above 6 gigahertz, for example, frequency range 2, I think it is, that goes up to sort of from 24. Once you're into the millimeter bands, things are extremely different. We would need to adopt new propagation models. We'll need to investigate those models. So the process really becomes entirely different. But if you're doing, if you want to deploy 5G at, let's say, 2600 megahertz, a lot of the principles that we apply in LTE could be applied across 5G as well, with some caveats, shall we say? Okay. Any more?
Yeah, well, I've got a few questions on my side as well, but of course, to everyone joining us, if you have any burning questions of your own, feel free to post those in the question section just to the side of your screen. One question I've got is, so you mentioned that cell edge throughput could be as high as 5 to 10 megabits per second. So is this not a bit too high?
Yeah, if we were planning a typical macro cell, so if we're looking for a 5 to 10 or 15 kilometer radio cell, then 5 to 10 at the edge is probably a little bit too high. But the reason I would say 5 to 10 megabits per second is because if we're deploying in urban centers, the cell sizes will naturally be much smaller anyway. And if we can keep control over the signal to noise, we can have at the edge of the cell a much better modulation coding scheme. So maybe we could even get a 16 QAM at the edge of the cell. Now the edge of the cell in this case happens to be relatively close to the center of the cell, so maybe only a few hundreds of meters, and it seems reasonable under those circumstances that we can get much higher cell edge throughput. Because by optimizing a system for high cell edge throughput, it does make the cell smaller, but it increases the overall capacity of the of that system.
Okay, brilliant. And then one last question I've got. So how does carrier aggregation change the planning process? For instance, the impact on link budget and capacity planning.
Yeah, well, clearly the one thing that carrier aggregation does for us is massively increase the capacity of the system. But in a planning sense, what we can do is to address each individual component carrier of carrier aggregation and say, well, what contribution does it bring? So if I've got 3 20 megahertz channels, all from more or less the same spectrum band, we can still dimension the cell in terms of its coverage in the same way, but now we can effectively got 3x increase in capacity. Now it may not be quite as simple as that, because there are additional overheads. There's control channels, things like PDCH planning that we would need to do in a carrier aggregation scenario, but one of the slightly more complicated things about carrier aggregation, and one of the things it's extremely useful for, is using very diverse frequency bands. So if I've got, say, 3 component carrier aggregation from the 700 megahertz band, the 1800 and the 2600, then clearly each of those component carriers will provide a different amount of coverage, and that's something that would need to be considered in a planning process. But you could treat each radio channel as its own and say, well, okay, how big will the 700 channel be? How big will the 2600 be? And then you can get a sense from looking at a cell plan then, just at what point in the radio cell can we use only a single carrier, then 2 component carriers, and then maybe when you're very close to the center, we might actually have access to 3 component carriers. That would only really be the case where the spectrum bands are very different. But yeah, so it's not so complicated, I would say.
Okay, and let's say, so two more quick questions. So that've just come in. So what is the impact of LTE-M or MB IoT on LTE planning?
Yeah, that's a pretty good question, because narrowband it does give us some advantages in the link budget. Now we would be making maybe quite a lot of assumptions about the environment in which we're planning this system, but IoT, let's say agricultural IoT, for example, narrowband services have a link budget advantage because they don't occupy quite so much spectrum. So the distances, the ranges that we expect to see out of a machine-to-machine type service will be much better than if what we're doing is like just a blanket mobile broadband plan. So I mean, you can connect, of course, machine type communication services based on LTE. They could be connected back to an existing site. So if you've already planned your network and all your sites are already in place, then your main concern, I think, would be how will that change the traffic profile of that particular radio cell? So, how much narrowband or how much IoT information is there to convey, and at what times of the day would we be polling those devices? If you were doing a greenfield plan, then you could probably do it quite cost effectively, because the size of the cell will be very much larger than it would be for a mobile broadband system. So there are impacts based on both capacity and coverage. I think that was from Jacques.
Yeah, that was from Jacques there. And so our last question from Dave. Will the building modelling predict potential screening or shadowing in built-up areas, city centres?
Well, yeah, yes. If you've got the right software tool and you've got the right model information, so if you've got sort of three-dimensional models of your city that have embedded in them the RF properties, then yes, it will do that. It very much depends on the software tool, but there are techniques called ray tracing, which Dave, you might have heard of. They use it a lot in 3D gaming, where basically what you're doing is predicting a photon path, and you see where that photon goes and what it collides with. So if you've got RF information and 3D models about the buildings, you can use this sort of ray tracing method to predict screening, shadowing, building penetration, losses, and so on. So you can absolutely do it, but it's very time consuming, and it's extremely expensive because you need both the models and you need a fairly big computer to sort of to do that processing as well, because it's time consuming in computer processing time. So the simple answer, yes, you can do that if you've got the money, sure, and the time.
Okay, brilliant. Well, I think that's all we have time for today. I'll just answer some quick questions regarding the training material. So Reno asked if we can get a copy of the training material. So yes, so if you look in the resources list to the right of your screen, you'll be able to download the presentation slides from this session. We will also be sending out the recording for the webinar. So if you want to look back on what Dave has discussed during the webinar, you can feel free to do that in your own time. And just to follow up on the course as well, so as Dave mentioned, we are going to be holding a 5-day boot camp in both Johannesburg and London. So again, if you do want to get a bit more of an in-depth understanding on this subject, then that could be a very good opportunity to do so. So yeah, feel free to contact me if you have any questions regarding that. But yeah, thank you so much, Dave, for a great session there. And yeah, if anyone submitted any questions that wasn't addressed, keep in mind that Dave will be in touch to reach out to you directly. And before you log off, please take a moment to complete the feedback form so we can continue to improve your digital, your experience with our webinars from the Telecoms and Tech Academy. But on behalf of the team here, I'd like to wish you a very good day. And yeah, I hope to be joined again by you soon. Okay, thank you.
Thanks, everyone.